In section 1.5, we're going to look at some of the applications of quadratic equations. For any of these problems, it's important that we spend some time thinking about what the problem is representing, devising a plan on how to model the situation with a mathematical equation, then carefully solving the equation, and finally revisiting the problem to make sure that what appears to be a solution actually works in the context of the problem. Let's take a look at a couple of simple examples to start. Here we have that the product of 6 and the square of an unknown number is equal to 24. Well, we know that the number has to be squared, and following the order of operations, let's go ahead and take care of that first. The square of a number can be represented as x squared. The product of 6 and the square of a number can be represented by 6x squared. And we're told that this is equal to 24. Pause before moving forward and make sure that this equation adequately represents the problem that we're trying to find an answer to. The product of 6 and the square of a number is equal to 24. I'm pretty satisfied that this looks correct. Now, solving the equation is the easy part. To solve for x, we'll first divide both sides by 6, so we'll get that x squared is equal to 4. And then we'll use the square root property to say that x is equal to either the principal or the negative square root of 4. Therefore, x is equal to either plus or minus 2. That means that there are two solutions to this problem. The number could either be negative 2 or the number could be positive 2. We'll write that in set notation. In the next example, we're told that the square of the difference between a number and 9 is 9. Difference indicates subtraction, so we'll first look at the difference between a number and 9, and we'll write that as x minus 9. Then we're told that the square of this difference, so the square of the difference, is equal to 9 itself. Again, pause and make sure that what we have adequately represents the situation that we're trying to model. The square of the difference between a number and 9 is equal to 9. It looks pretty good to me. Using the square root property, we have that x minus 9 must be equal to either the principal or the negative square root of 9. So that means that x minus 9 is equal to either positive or negative 3. To isolate x, we'll add 9 to both sides, so we'll get that x is equal to 9 plus or minus 3. So there are two solutions here. Either x is equal to 9 minus 3 or x is equal to 9 plus 3. In one instance, we get that x is 6. In the other, we get that x is 12. That means that we have two solutions to this problem. Either x is positive 6 or x is positive 12. Now, in both of these examples, we were just working with unknown numbers. There were really no restrictions on what those numbers needed to be. In the next objective, you'll have problems where we're using projectile motion models, and we have really good examples in your digital textbook, in your e-text through my math lab, that covers the material very clearly. Make sure that you go into your multimedia library in my math lab to watch these videos. Let's take a look at another example involving geometry. This one's going to be pretty involved, so make sure you leave plenty of space in your notes and make sure that you put your thinking caps on. We're told that a 22-foot by 28-foot rectangular swimming pool is surrounded by a walkway of uniform width. If the total area of the walkway is 216 square feet, we have to answer the question, how wide is the walkway? In order to get started, I'm going to draw what that swimming pool might look like. We have 22 feet for one dimension and then 28 feet for the other. So let's say that this side is 22 feet and that this one is 28 feet. Now we have a walkway that goes around the pool and it has uniform width. That means that the sidewalk, if you want to think of it as a sidewalk, is of the same width all the way around. Now we don't know what that width is, that's exactly what we're trying to find, but we can label it as the unknown quantity x. So we'll say that the walkway has a width equal to x. Now, this is true all the way around, so this will be x as well. Now, let's think about the total area of the larger rectangle that includes the walkway and the pool all together. And then let's compare that to the area of just the pool. If we subtract the two areas, we should end up with the area of just the walkway. This kind of looks like a picture frame. So think about it as the area of the entire picture frame and the picture inside. And then we take away the area of the picture. That leaves us with just the area of the frame. So let's write what these two areas would look like. So total area of the walkway and pool combined would be the area of the larger rectangle. And let's see, one side would be equal to 28 plus 2 x's. Let's see if I can convince you of that. So from corner to corner, we've got 28 for the pool, and then we've got an x here on the left and an x on the right. So I think the total width would be 28 plus 2x. So that would be one of the side lengths of that larger rectangle. For the other side, we have x here at the bottom, x here at the top, 22 here in the middle. Let me see if I can repeat it on this side to make it easier to see. So from top to bottom, I think that length will be 22 plus 2 x's. So we've got the 22 in the middle, and then x at the top and x at the bottom. That means that the total area of the larger rectangle would be 28 plus 2x times 22 plus 2x. And that'll be in square feet. Now, if we subtract from that the area of the pool, we should get the area of the walkway. So let's find the area of the pool. The area of the pool is equal to 22 times 28. That means that the area of the walkway would be equal to the area of the big rectangle, 28 plus 2x times 22 plus 2x minus 28 times 22, and we can write it backwards. I didn't mean to, but thankfully multiplication is commutative. We can multiply in any order and get the same result. But this is the area of the walkway. The total area of the larger rectangle minus the area of the pool gives us the remaining area, which is the area of the walkway. Now we're told in the original problem that this area is 216 square feet. So now we just need to carefully write this as an equation by setting this area equal to 216 and solving for x. I'm going to continue this problem in another video because I'm out of space, but play the next video for section 1.5 and we'll take this one home.